Hey guys, how's it going? Mike coming back at you with another video on discrete mathematics. In the previous video, we got a little bit of an introduction into properties of sets. I just stated a few basic properties. We saw some basic definitions for what it means for an element to be a part of one of our special sets. And then we saw how do we show that a particular set is a subset of some other set, and we went through a sample proof of that. In this video, we're going to see some more properties, and we're going to see how we show that two sets are equal to each other. So as I said, we have some more properties or some more identities for equality of sets. Given a universal set capital U, and then we have sets capital A, capital B, and capital C in that universal set. First two properties here, commutativity and associativity, hold for sets. The order in which you take the intersection of two sets does not matter. And associativity, as long as you're taking the union or the intersection of all three sets, it doesn't matter where the parentheses go. In fact, in some cases, you might not even see the parentheses being written, but if they are written, if they're all unions or they're all intersections, then it doesn't matter where they go. 3, the distributive property for sets. Very similar to the distributive property for the disjunction and the conjunction. A union B intersects C is equal to A union B intersect A union C. And similarly, A intersect B union C is A intersect B union A intersect C. So the A and the symbol that follows gets multiplied, if you will, in air quotes multiplied, to each of the letters inside. And then those things that are in parentheses on their own get separated by the other symbol that was inside of there. 4, the identity. If you're going to take the union of A and the empty set or the null set, you're just going to get A. Similarly, if you take the intersection of A and the universal set U, then you get the set A. 5, the complement property. If you take the union of a set and its complement, you're going to get the entire universal set U. If you take the intersection of a set and its complement, you're going to get the empty set or the null set. 6, again, it should look fairly familiar, should look pretty similar to something we saw regarding laws of logic. The complement of A is just A. 7, the idempotent laws. A union A is A, and A intersect A is A. Those things just kind of make sense. Universal bound laws. A union the universal set U is equal to U, and A intersect the empty set is going to give you the empty set. 9, the De Morgan's laws. What's the complement of A union B? Well, it's the intersection of the complements of A and the complement of B on their own. This is very similar to the De Morgan's laws for taking the negative of a conjunction or a disjunction. The negative goes to every letter and the sign switches. Same kind of thing here. The complement goes to each of your two letters. And the sign switches. Similarly, if you had A intersect B and you want to take the complement of that, it is the union of the complement of A and the complement of B. 10, the absorption law. A union A intersect B is equal to A, and A intersect A union B is just going to give us A. Those things are a lot easier to make sense of if you draw some Venn diagrams. 11, the complements of the universal set and the empty set. The complement of the universal set is the empty set, and the complement of the empty set is the universal set. And then 12, we have a way to write the set difference in terms of intersections and a complement. A minus B is equal to A intersect B complement. So those are the properties that I wanted to show you in this video. Now I want to go on to how do we prove that two sets are equal, and we're going to see this with a sample proof. Really all you're doing when you're showing that two sets X and Y are equal, you're just showing that each set is a subset of the other. So you're going to start off by showing that X is a subset of Y, then you're going to show that Y is a subset of X. The only way that two sets can be subsets of each other is if those two things are the same set. And we're going to prove one of our De Morgan's laws. We're going to show that A intersect B complement is equal to A complement union B complement. So first thing, I'm going to pick some arbitrary guy in this set here, and I'm going to show that it lies in that set there. So hence I start off with let X be in A intersect B complement. Well, by definition, what does it mean for X to be in the complement of some set? By definition, it means that X is not in that set. So saying that X lies in the complement of A intersect B means that X is not in A intersect B. And this is where it gets a little bit odd, and maybe it's not the most obvious thing to see how you would jump to this. But if you think of what this is saying in terms of logical operators, if you think about what this is saying in terms of disjunctions or conjunctions, saying that X is not in A intersect B is saying not X is in A and X is in B. It's saying the negative of that right there. So by using the De Morgan's laws for logic, this is not X is in A or not X is in B, which is saying X is not in A or X is not in B. Well, by definition, X not in A means that X is in A complement. And then similarly, X not in B, by definition, means that X is in B complement. So we have X is in A complement or X is in B complement. If X lies in this guy or it lies in this guy, then X lies in the union of those two guys. So that's why we say that X lies in A complement union B complement. So we've now shown half of what we've had to show. We've shown that this guy is a subset of this guy. Now I want to let X be in this guy and show that it lies in this guy. And because we're using definitions and they're if and only ifs, the reasoning is basically the same. We're basically just going to go in the reverse order, but I've just provided a little bit different wording on the second half just to maybe make it seem a little bit more clear. So I want to show this now. I want to show that the union of the complements is a subset of the complement of the intersection. So I let X be in this guy here. I want to show in the end that X will lie in here. So since X is in the union of two sets, X lies in the first set or it lies in the second set. So X is in A complement or X is in B complement, which in turn by definition means X is not in A or X is not in B. But saying this right here, X is not in A or X is not in B, is the logical equivalent of saying not X is in A and X is in B. So we know from what we've assumed that not X is in A and X is in B is true, which means that saying X is in A and X is in B, just saying that is false. So if we know that it's false to say that X is in A and X is in B, then we're saying that it's false that X is in A intersect B. So we say X is not in A intersect B, and therefore by definition X lies in the complement of A intersect B. So now we've shown that this guy is a subset of this guy. And thus we've formally completed our whole proof. We have shown that these two sets are the same thing. And yes, it may seem a little bit repetitive going through that second half because we're using the same logic just in the opposite order. For our sakes, just getting used to proving things, although it may sound repetitive, still write those things out separately. Just because this will help you see the structure more, and this will really help you just get your feet wet with these proofs, and it will make your life a lot easier, and these things will seem more familiar to you when you take a higher level course, when you have to do a lot more proofs. So we've shown that these two sets are indeed equal to each other, and that is our sample as to how we show that two sets are equal. You're just showing that each set is a subset of the other set. So this concludes our video on properties of sets. If you have any questions or comments, be sure to drop them in the comment section below. And guys, take it easy.